Hello and welcome to the last part of our videos on section 16a about tangents and normals, and we're going to look at a couple of questions from your textbook that are a little bit more difficult. So for example, finding the equations of horizontal tangents to this expression. So the steps are the same. We need to take the derivative and then evaluate it at a particular value of x to find the value of the slope of the tangent. And then we can write the equation using that slope and the point that we care about. But here it's a bit trickier because they didn't give us an x value that we care about. They just want us to have horizontal tangents. So let's start by finding the value of the slope of the tangent. So I'm going to take my expression here and find the derivative. It's not a very difficult derivative to find, luckily. So we have a gradient function that is a quadratic. And then we need to remember when tangents are horizontal, that means that their slope is equal to 0. Okay? So we're going to set this whole function equal to 0, and we're going to solve for x. So we're going to use a factoring strategy, common factor out of 6, factor this simple trinomial, and we find out that x could be -2 or x could be equal to 1. So there's actually 2 spots on that curve where we have horizontal tangents. If x was equal to -2, then we can plug in -2 to our function to find the value of y, so that we now have a slope and a point. Okay, remember that the slope is 0, but we need the value of the point to find the y-intercept. And likewise, when x equals 1, we need to find the value of y. So where's the point where the slope of the tangent is equal to 0? Then I can sub that into my y equals mx plus b formula along with a slope of 0 and find the other y-intercept where this has a horizontal tangent. Okay. And remember that the equation of a horizontal line is just y equals something. So those were our equations. We're also going to look at 3b, find the points of contact where the horizontal tangents meet this curve. Again, if we're not sure what to do in calculus, the best thing to do is to start by taking the derivative. So we're going to take the derivative here, starting by rewriting this with exponents instead of with radicals. When I take the derivative, remember that that 1/2 is going to drop down. Same thing here, the -1/2 is going to drop down. We're going to reduce our exponents by 1. We end up with a derivative of 1 over root x minus 1 over 2 root x cubed. I'm going to set this expression equal to 0. And notice that once I do that, I've got a fraction. I've got 2 fractions here, so I need a common denominator. So I'm going to multiply both. I'm going to take this term that's simpler, and I'm going to multiply it by 2 times the root of x squared to get a common denominator of 2 root x cubed. That's going to give me 2 root x squared in the numerator here, minus 1 from the numerator over here. Now, we can eliminate the denominator, and that's because for this whole fraction to be equal to 0, it means that the numerator has to be equal to 0. That's the only way that this expression could be equal to 0. So I can kind of ignore the denominator. And then I can solve for x. Now, that means that I can, root x squared is just the same as x. And then I can bring the 1 over, divide by 2, and find out that x is 1/2. Now I know the point where the x value, where we have a horizontal tangent. So I'm going to plug that into my original expression. Okay, original expression up here. And I'm going to solve for y. So when I plug in 1/2, I get 2 times the root of 1/2 plus 1 over the root of 1/2. I do a little bit of algebraic manipulation here. So what I started to do is try and get a common denominator by multiplying both by the root of 1/2. Luckily, that helps make this get rid of the radical up here. And I simplify a little bit more, and I end up with this expression. The point is 2 root 2, and there is the point of contact. If you have any questions, we can review this radical operation in class. Thank you, and have a great day.